So, today we're going to talk about phase transitions. So, we're going to start to talk about phase transitions. So, basically, what you saw in the normal, I hope you had the simulation. So, it was a very specific case. We're going to see different cases, but you had some grid. Now, some of the spins, you start at some initial case with some of the spins up and some of the spins down. So basically what happened when you have a phase transition is that if you look at that case, at temperature that's low enough, you have the spins want to align with each other, and the reason that you need the low temperature is because it needs to compete with the fluctuations. So if the fluctuations are too strong, it's not going to happen. But basically, if the temperature is low enough, this is going to the spin going to start to align with each other. So so you're going to have like kind of clusters. I'm not going to draw it very good, but you understand. So you're going to have clusters. So like you have a lot of minuses here, and then a cluster of pluses here, and then. So in the beginning it's going to look like that, and then eventually the cluster is also going to flip, and you get a case where all of the spins align in the same direction. So this is the phase transition. So what we're going to discuss today is what are the conditions to have a system with phase transition. So we already saw one system that we have phase transition, which is two-dimensional Isaac model. So we already know that that works. But let's look at some other cases. So let's start with the simplest case, which is one-dimensional Isaac model. So we have a chain of spin of size n, and what we're going to look at is the last stage of the phase transition. So I'm going to have two clusters, with one-dimensional clusters, but still. So all of those spins are going to be up, and all of those spins are going to be down. And I have this. I have a domain wall in the middle, like not an actual domain wall, but you understand. So I want that system to go into that system where all of the spins are aligned, let's say, down. So the condition for that to happen is what we want to see in physics in general is we want to minimize the energy. Specifically here is the free energy, not specifically here, but specifically here we're going to look at the free energy. So the free energy, it includes the regular energy that we know from the Hamiltonian, that we're going to see exactly what it equal to, and the entropy. So you know that from like thermodynamics and in general, I hope. So if you minimize this free energy, you maximize the entropy and minimize the internal energy. So this is what we want to do. So let's calculate the free energy for that case, and for that case, actually the difference between them, and see which state is more, which state the system we want to choose. So the difference in the free energy, let's say it's the free energy of the disordered case, so let's call it Fd, minus the free energy of the ordered case, so that's Fo. So if that is smaller than 0, it means that the disorder case have lower free energy than the other case. Therefore, we don't have phase transition. So no phase transition, because the system will prefer the disordered case. If this is larger than 0, it means that it will prefer the ordered case, and then we do have phase transition. Okay? So this is what we're going to look at through this whole tutorial. So this is important.
Because if it's in order, that means?
Order is like that case, where all of the spins align in the same direction. So whichever case have the lower free energy, that's
why we're not expecting phase transition to occur there?
What? Sorry?
Why we're not expecting phase transition to occur?
We don't expect if the free energy of that case is lower than the free energy of that case. Because we always minimize the free energy.
Mm-hmm.
Okay. So, for example, in the case of the, we're going to mention it again later, but in the case of the two-dimensional case that you saw in the homework, if the temperature will be higher, the entropy part will be more dominant, and then, okay, we'll see. But anyway, this is the general condition. So what is the free energy for this case? So the difference in the internal energy, so we remember that the Hamiltonian of the system is that you don't have any external magnetic field. So the only difference is those spins, right? Everything else is the same. So those spins in that case are going to give me interaction of, they have opposite sign, so they're going to give me factor of J. Versus this case when they have the same sign, so they're going to give me minus J. So the difference between both cases is just 2J, right? Because we take that minus that. Now, what about the entropy? So for the entropy, we're going to look at the number of states. So in general, the entropy is the logarithm of number of states. We call it omega. So for the ordered case, we have basically just one option, unless we just switch the location of the spins, but that's not, doesn't matter. We only have one option for the way the systems look. All of the spins align down. We actually have either all of the spins align down or they align up, but that's just equal to 2, but 2 is a very small number, so I'm going to ignore it for that second. But for this case, we have the location of the domain wall. So the domain wall can be basically anywhere in the system between any two spins. So it's have approximately it's have well, I'm going to write it. So n-1 location places to be. So the overall number of states is approximately logarithm of n. So we are going to look at, I don't know if I mentioned it in the beginning, but we're going to look at systems that are very, very big, systems that go to infinity. So n go to infinity. This is very important. So that's why I'm ignoring the 1. Okay, so we have everything we need for the free energy. So delta F is equal to 2J minus T ln n. So J is a number, is a finite number. If it's infinite, this is very different system, but it's a finite number. T is a finite number, and n is something that goes to infinity. So that it means that no matter which for any finite temperature that I'm going to choose, that expression going to be smaller than 0. So this is always smaller than 0 because the logarithm of n always going to dominate the free energy. So the conclusion of that is that there's never no phase transition in 1D. Okay? So that's actually one case. Okay, we're going to do like different type of cases, and I put in the Moodle like a table with all of the different like dimensions and different stuff that you can have. So this may help. So the obvious thing would be to go to higher dimensions. You saw in the homework, but before that, let's try to do something else. Let's try to change the interaction in the system. So we still have 1D. But we now add long range interaction. So what does it mean? So let's say we had the J between the nearest neighbors. So we call it J1. But we also have J2 for the nearest, the next nearest neighbors. And then J3 for the next nearest neighbors, and so on. Such that in general, we can write the coupling between two spins as a function, as function of r, that is the distance. It's a discrete distance, but it's a distance. It's proportional to r to minus sigma. Sigma is some number for now. So we have long range interaction. The interaction decays with r to some power. So we still have a domain wall because phase transition still behave as phase transition. So this is down, this is up. So the entropy not going to change because the only thing that's related to the number of states between that and the ordered state is the location of the domain wall. So the entropy is the same thing. So delta S is still ln n, but the internal energy is going to change. So what's going to be the difference in the energy? So for J1, we still have factor of 2 because this is similar to before. Now for J2, we have actually So for J1, we only have the interaction between those two spins. But for J2, I have the interaction of this with this, in the interaction of this with this. If we compare like the difference between this to the case where all of the spins align. So I'm going to have 2 multiplied by J2. And then if I go to the next interaction of where I have like, I look at like 3 spins away. So this one interacts with this one, and then this one with this one, and this one with this one, and you start to, yeah, and I think that's it. So you're going to have 3J3, and so on.
What is the rule of counting?
What?
What is the rule of counting?
How many pairs you have? So
Okay.
for the
But
nearest,
it's infinite long? No. Yes?
yeah, it's infinite to both directions, but the number of pairs that have different sign. So because this is compared to the case where everyone in the same
Okay,
direction.
okay, I see.
Okay.
Yeah.
So in the first case we only had that, but now we had further interaction, so we have additional terms.
Yes.
So in general, if we have we can write that as a summation over Ri multiplied by 2 j of Ri. So we have the distance multiplied by the coupling at that distance. So if j of r, we assumed in the beginning that it's proportional to r to minus sigma. So this is summation of r1 minus sigma. Now, what we are looking at is actually the interaction in very far distances. This is what we're interested, because this is the part that we're going to contribute mostly to the energy. So we assume that R is very large, larger than R1. So we're going to approximate this summation into an integration. So we have an integral from 0 to the size of the system, which is n, R1 minus sigma, and this is approximately going to be n2 minus sigma. I'm ignoring additional factors. So this is delta E, and we already see that we got something that depends on n. So we have something that may compete with the logarithm of n that we have in the entropy. So the overall difference in the free energy is n2 minus sigma minus t ln of n. So so if we have two cases here. So if sigma is larger than 2, we see that this is going to be decay to 0, where n go to infinity. Right? So n2 minus sigma, where n go to infinity, going to decay to 0, because this is going to be negative exponent. If sigma is smaller than 2, this is going to go to infinity.
You want 0 instead of 2.
Right? Smaller than 2. So this is going to diverge to infinity, and actually this part is going to be stronger than diverge to infinity, larger, faster than the logarithm. And well, so okay, I will talk about sigma equal to in a second. So what actually happened is that you see that the part that determines if the free energy is going to switch side to switch sign. So if sigma is larger than 2 and that part is going to be negligible compared to that, we're still stuck in the same problem as the one-dimensional normal interaction. So we have no phase transition because it didn't solve anything. But in the second case, if sigma is smaller than 2, the decay of the interaction is very, very slow. And then this part overcomes this part, and we do have phase transition, because this goes to infinity faster than that. So this is for larger and smaller. For sigma equal to 2, we can't see that here because you need to add like logarithmic corrections and stuff. So I'm just going to tell you that you do have phase transition. So this is just. So this is just given. So what we saw is that you don't have phase transition in 1D, unless you have a very slow long-range interaction. Questions? Okay, so let's solve question. So this is from 2020. Question 1. Okay, so you have, okay, the first part is not, okay, so you have an Hamiltonian interaction that depends on the distance between the two spins, between I and j. So this is basically j of r that we defined earlier. And the system I'm going to write different options for this function. And the question is which following system so which ones of those following systems undergo a finite temperature phase transition? So the first option, so j of r is equal to so sine of r square over r. So okay, so what we said in the beginning is that what we said earlier is that we're going to look at r that is very large because we want to look at the long range function. So we want to see how this function behaves when I take r to be a large number, and how it actually decays with r, and then we're going to compare it to what we know. So if r is very large, so sine of r is a periodic function, so it's just going to give us a number.
It averages to half.
What?
It averages to half.
Yeah, but we don't average, we take a limit.
Okay, but for large enough r.
If you want to write a half, you can write half. But basically for us it's just a number. Let's call it C. So everyone can put their favorite number. And R just remains R. So this is actually decay as R to the power of -1. So if you compare it to the general case that we saw of R to minus sigma, this is just a case of sigma equal 1. Sigma equal 1. So sigma equal 1 is clearly smaller than 2. So we do have phase transition. So phase transition.
What were you saying, man? That for large enough r, it goes like...
It's go like as r to -1. The case is r -1.
Okay.
Okay, so this is the first case. Okay, second one is j of r equal to 1 over r hyperbolic sine of e to the power r. So
Finish of E to the R. Okay.
so
It's like
let's
an
first.
infinite sigma.
It's like E to the R.
I didn't say.
I said it's like saying it has infinite sigma.
Well, yeah, but wait. So this is equal to so R remains outside, and we have E to E R plus E to minus E R, and then if R is very large, the second term decays faster, so we can ignore it. It's negligible compared to the first one. Then this is approximately E to minus E R over R. So this one decays. So you see that this decays faster than exponential. So this is not even a power law. This is just an exponential decay. So this goes to zero like immediately. Then sigma is really kind. Yeah, it's go to infinity.
It's less than every
And-
polynomial decay.
Yeah. So sigma go to infinity. Then we have no phase division. So the last case, we go there because space. J of R. So R cube and then square root of 1 plus R to the power 5 and R to the power 10. So if R is very large, 1 is negligible compared to that, and R to the 5 is negligible compared to R to the power 10. So this is just R to the 5. So this is R to minus 2. Sigma equal
That
to
will
2.
go.
Yeah, and we saw that this is like the boundary case. We do have straight division. Okay, so this is a very technical type of work in those questions.
Practically for sigma equal to 2, n to the power of 2 minus sigma is going like a lab. That's why it's balancing, right?
Mhm.
For sigma approximately goes approximately 2, n to the power of 2 minus sigma is approximately ln of something. In order.
You have you just have logarithm correction to that because
Yeah,
that is
that's what they
approximation.
said, that will match the.
Yeah, and then it's matched, and then what you have is something that behaves like just like a two-dimensional system that we're going to discuss in a minute.
Okay.
So. Okay, so all of that for one dimension. So what happened? So what happens when we go to higher dimensions? Okay, so Pierre's argument, you basically saw it with Ido, and if you didn't, you see it next lecture. So it's basically applied for two-dimension case, but it's also, but you can also use it for higher dimension, but we're only going to two-dimension. So we do something similar to what we did for the one-dimension case. We look at the system, and we have some domain in the middle of the system. So let's say everyone minus, and inside everyone R plus. So now the domain wall is between the area in the middle to everything else. So this line is of length L. So we still compare the free energy, and in that case, the difference in the internal energy, you have the interaction between any pair on the boundary of the system. So you have 2j multiplied by the number of pairs, which is the length of the boundary. So this is L. And for the entropy, we're not going to prove it, but other people proved that the number of different possibilities to build such a boundary in the length L is actually proportional to e to the power L. So from that, the difference in the entropy is going to be proportional to L. Actually, you have a coefficient, so I'm going to put C for units. It doesn't matter. So delta F is equal to L to J minus CT.
Talia, I know we are physicists, but it's not either side it's something 2.7, but it's not exactly.
That C is 2.7?
Oh, C. There is C there. Okay.
Yeah.
Shouldn't the boundary be for L? Because like you have L. Shouldn't the boundary length be for L? Because
No, I called all of it L. But
okay.
it just gives you a factor, so it doesn't matter. But yeah. All of that tutorial, we look at like order of magnitude of stuff. So. Okay, so basically what we see is just that both of those scales with L. So this is a number and this is a finite number. So what happens is that you see that you do have phase transition for some values of the temperature. So you have phase transition for T that's smaller than some critical T, and you find the critical T by comparing those two terms, and this will give you what you got in the homework. So if you look at the magnetization versus the temperature, you see that if you look at the lower temperature, you have this transition of the spins aligned to one direction. If you look at high temperature, you get it. It's not, and in the middle you have stuff that relates you to the fluctuations of the system. So this is what we're going to get. Yeah, so this is also can be applied for higher dimension, and then so basically for any dimension that's larger that's 2 or up, you're going to have phase transition for any normal type of interaction.
It's D times C.
What?
It's DC.
Yeah.
So it's not the same C. I was just confused with.
You took the logarithm of that to get, this is the number of.
C is a number, right?
Yeah, C is a number.
And T less than.
Oh yeah. Sorry, this is like T critical, and this is C 0.
Okay.
You can drop C if it bothers you. We don't care about units here.
Can you please repeat what you said about higher dimensions?
About what?
Higher dimensions.
Yeah, so basically you can just generalize it to higher dimension. So you have phase transition for D that's equal or larger than 2. So I think for higher dimension this argument have a different name, because every time physicists do something you just name it after him, but it's basically the same thing. Okay, so for the last and most interesting, maybe type of models, so let's look at So now let's look at what happened when I add an external magnetic field. So it's a bit bigger. So let's say I have a random magnetic field. So I have the Hamiltonian minus J Si J. I'm still in 2 dimensions. Minus Hi Si. So the magnetic field is inside the summation, and Hi can be, for example, plus minus some epsilon. And epsilon is very small compared to J. So I have plus minus epsilon fields through the system. So now what happens? So if the field is not very weak, this is going to be like a different problem that we're going to discuss in the later part of the course, but you can see that it's going to affect more significantly the system. But if the field is very weak, it's not necessarily going to destroy the phase transition because we're going to see. So let's look at the domain as we did before. So I have a domain here with the pluses and the minuses. So yeah. Okay, so if I don't have any external field, we saw that what's going to happen is that eventually all of the spins that align to the plus direction inside this domain are going to flip back to minus, and you're going to get phase transition. But what happened if, so this field is random, which means I'm going to have clusters in the systems where I have some place that I have more plus epsilon than minus epsilon, or the other way around. So let's say I have here within this domain more plus epsilon, so I have plus epsilon, minus, but mostly plus. So now I have, so the system going to want to align with the neighbors on the one hand, but they also want to align with the magnetic field on the other hand. So you have two competing energies in the system. So let's look at them like separately. So you have the difference in the energy as a result of the coupling. So we saw that for the 2 dimension, but in a general dimension D. So let's change it to D dimension. So in a general dimension D, this is going to be proportional to LD minus 1, because it's going to be proportional to the surface of this area. So if I look at 2 dimension, the surface is going to be 1 dimension. If I go to a higher dimension, it's going to be 2 dimension. So the interaction is only on the boundary, so this is going to be proportional to that. On the other hand, you have the energy, the contribution of the energy from the competition with the magnetic field. So let's call it E bulk. So what is this energy? So in general, we have, this is going to be the summation over all of the multiplication of the field between the spins. And we know that basically half of those are going to be up, like half of those are going to be plus and half of those are going to be minus. So on average, this is 0. But we look specifically, the reason that this cluster exists here is because we know there is higher concentration of either pluses or minuses here. So what we want to look at is the fluctuations of Hi around this minimum. So if you go back to like statistics course and stuff, so from the central limit theorem, the fluctuations of the sorry, the fluctuations of the average going to go like the square root of
variation.
Yeah, of so here it's L to D in that case, because this is the, so let's do it. This is going to go like
Talia,
what?
they are not correlated.
The what?
There is not a correlation between
the field.
the HI and the cell. No.
Yeah, this is IID. They're not. Yeah, they're all independent. We assume that they are.
Identical.
Yeah, identical independent.
Distribution.
Exactly. So if you don't remember that or something, like it's not very important. But if you do, you just remember this whole like square root of the number of variables that you have. So this is going to be the number of particles, where n in that case is the number of spins inside the bulk. And this is equal to square root of L to the power D. So this is going to give you the volume of the bulk.
No, but you need to multiply it by epsilon squared. Inside the square. Okay. Epsilon is just a factor. Okay.
I'm ignoring. You also have like J here. I'm ignoring factor. Just look at the dependence of L. But yeah.
Okay.
Okay. So overall, delta E is, cannot write equal. This is approximately the difference between LD minus 1 and LD over 2. So where the energy from
it's not working like that.
What?
It's not working like that. One reason is units, but okay, with some factors.
Yeah, this is. I use Proctor. This allows me to ignore units. That's the rule. If I use that, I have to keep units. If I use that, I can ignore units. That's the rule. So it's proof. So okay, so if
you feel great with that?
Yeah.
She's experimentalist, so.
Oh.
More than that, she's a very fair student.
Just tell him photons and that's all.
Okay, sorry for interrupting.
So anyway, so if the first term is larger than the second term, it means that the energy that it takes to hold the spins against the interaction with the neighbors is more significant than the energy it takes to hold the spins against the interaction with the magnetic field. And if the second one is larger, it means that the interaction with the field is more significant than the interaction with the neighbors. So the critical dimension in that case is, surprisingly or not, equal to 2. So, but in that case, okay, so if D is larger than 2, there is phase transition, because it means that the first one is still dominant. If D is smaller than 2, there is no phase transition, because the interaction with the field is so strong that it's overcome the difficulty from the interaction with the neighbors. And if D is equal to 2, there is also no phase transition. So this is actually the only case that we're going to have a change, because for D smaller than 2, we don't have phase transition anyway, so it doesn't really matter. And for D larger than 2, we just keep having phase transition, so you know that's great. But for d equal 2, this is the only case where the external field actually going to destroy the order of the phase transition. So this is the main the main case that this have any effect. Okay. So basically, what you need to know is if you like the question in that case would be: is the system exhibit phase transition? Yes or no? So the conditions are. So let's write it. So. So the conditions to have phase transition is one, that d is larger than 2. 2 is that the average of the random magnetic field is equal to 0. And 3 is that the absolute value of the value of the magnetic field is very small, very weak compared to the coupling. So in that case, epsilon is very small compared to the coupling. Otherwise, it's no longer a weak magnetic field, and this is a completely different scenario to work.
So if the mean magnetic field isn't 0, so
yeah, so that was the assumption that we made. So we're going to have like larger corrections and none of that works anymore.
So you necessarily won't have phase transition, or it's just another question?
If it's not 0, so I think you're still going to have phase transition in the direction of the field.
If it's not 0, you can just shift it. You can assume, okay, assume they distribute the same. So you can write h equal to h0 plus some constant, and h0 will behave the same. But you will have some constant external energy
like
that
what
in
we
order
wrote,
of 1.
What we wrote was a correction to that go to 0, but so you're going to have something that's now go as to the power d instead of to the power d over 2.
Wait, what? Again?
Like the term that we add to the energy was something that go like L to the power d over 2, because that's the first correction from the central limit. But if the average is not 0,
what I'm saying is, if the average is not 0, you just need to add some sum of SI. What is the sum of all SI? It's like taking an external force of something.
But this constant probably is going to be proportional to the number of the spins, and then it's going to change this balance in the equation.
Of the spins.
Yeah, because you're going to have.
Yes. It will be proportional to the average of SI, sum of SI.
Yes. And then you have like something that go like that instead of that, and then it's always dominant.
Okay.
Okay, so those are the 3 conditions, and in addition to those conditions, you also have like I think we discuss about it a bit more later, but basically any condition that you have in general to phase transition. So I'll show you later, in like 5 minutes, I'll show you like an example so you see. But basically those are the conditions to phase transition for the case that you add an external one. Okay, so let's solve the question and then go home. Okay, so this is 2023. Okay, so you have different systems, and for each one. So the question is, will the system go the phase transition? So it's a finite temperature, second order phase transition. So the dimension is 3. And the Hamiltonian is, so you have like normal interaction, nearest neighbors interaction, and you have HI, SI. Okay. So the first is H, I, J, and K. You have, because you have 3 dimensions, so you have 3 coordinates, is equal to -1 to the power of I plus J plus K, multiplied by epsilon. And it's given that epsilon is very small. Okay, so from the conditions that we saw before, we have dimension 3, we have epsilon being small variable, so the main thing that we need to look at is the mean value of the field. So if we look at I plus J plus K, well, they're all like coordinates, so they go from 0 to n. So this is like just, like 3, 4, 5, etc. So this is just the natural variable. So half of them going to be even and half of them going to be odd. So for half of the time this is going to give me -1, and for half of the time this is going to give me 1.
But there are only 3 variables.
Huh?
But there are only 3 variables. AJK.
What?
You say half of them gonna be.
No, half of the result.
Okay.
Yeah, I, J, and K all go from.
Yeah, from symmetry of
Yeah,
the.
from 1 to n, or to n over 3. That depends, to some number.
For large enough.
Let's go to infinity. So you just get like 3 to infinity. So this is, yeah. So this is just the natural.
For large enough n, right?
Yeah. So this is going to give you 0, because half the time this is -1, half the time this is 1. Basically that's it. And so the second example is kind of similar. So you have -1 to the power of modulo function of, I think it's also, I plus J plus K modulo with 2. Multiplied by epsilon. So the argument is the exact same argument. I plus J plus K are going to give me the natural number. Half of the time, so J plus K.
But it's the same.
Yeah, so half of the time this is going to give me 1, and half of the time this is going to give me 0.
But practically taking mod is doing nothing.
Exactly, because it's giving me either half of the time it's giving me 1, half of the time it's giving me 0, half of the time this is going to the power 1 is going to be -1.
To write it to the -1 to the power of something is exactly writing it with the mod.
Yeah.
Okay.
So yeah, so half the time it's -1, half the time is 1. So on average, this is 0. Now to the last example, that's also not too different. And and then I'll just show you example from last year test to show you something that's a bit different. So this is -1 to the power of modulo of I plus j plus k with 3.
All the tests are published in the draft.
I don't know if all of them, but a lot of them, I think. Especially from last year.
Okay.
I don't know if the last one is, but if it's not, I can put it in the model or something.
Okay.
Or on the trial. So yeah, so we have modulo with 3, so in that case,
It will be 1, so that's
That this will be constant.
yeah, so
איך אני אומר את זה?
3. So
2 ו3 דברים.
yeah, so this is going to give me like you know, like 1, 1, 0. Like it's not going to be symmetric. It's not going to give me like half and half. So overall, h I j k is different than 0. Therefore, no flexibility. So yeah, question.
But if the average is not 0, that we say we didn't talk about that, but it still can go.
Yeah, technically right, but as far as you know from the course, it's not not going to. That's why I wrote explicitly the conditions, because we put the boundaries for what we're doing in a very specific place.
Okay.
If you think you do have phase transition and you can show it, I guess you wouldn't mind, but
it's a waste of my time. It will be a waste of my time.
Exactly. I'm glad that we agree. Okay, so the last example is not from this test; it's from last year's test, but it's just to show you, like, so in that case you had an Hamiltonian that let's see if I remember. So you had Si with this will take me a second. So Si j k with Si plus 1 j k, and then Si j k with Si j plus 1 k, and then the third one was something like Si j k and then I j k plus 1, and then this was multiplied with I j k plus 1. Let's say I plus 1 j k. Something like that, and then you also had the part of the magnetic field. So all of the point here is that the third interaction term is what's going to break the symmetry, because if you have something in the Hamiltonian that looks like that, the minimal energy of the system is going to be something very non-trivial, like not going to be necessarily something trivial. So the fact that the system not going to exhibit phase transition come from that, and not actually from the magnetic field. So the only thing that I want to say is that if you solve that type of questions, pay attention to the whole system, and like don't go like too technical, or like, you know, on like a autopilot, because you know it may hide in a different place. But yeah, so basically the conditions to have phase transition are specifically to the part of the magnetic field are the stuff that we said, but you can also have other conditions for phase transition that we're also going to discuss later, but they also like can be hidden in that type of questions. So that's one thing. But we go back to that. So this is basically about phase transitions from the perspective of conditions for phase transitions, and what we're going to do I think next tutorial and maybe the one after that is to talk about what actually happened in the face musician itself. So that's it.
That is done. הכלים שלנו במכניקה סטטיסטית הם לא תקפים רק כשאנחנו בשיווי משקל. כשאנחנו במעבר פאזה אנחנו מחוץ לשיווי משקל.
כן, בגלל זה אתה לומד את זה בצורה ספציפית, ובגלל זה זה כל כך בעייתי, לא יודעת לקרוא לזה.